This is another example of a video that I don't really have any music to play for you because it's about some pretty nasty stuff. It's about chemicals that we've discovered in the environment that does significant harm to humans. This is going to be a very long video, and that's why I scheduled it over the 3-day weekend. I suggest that you watch it sort of in pieces, and there's not a lot of slides to show you, but there's a lot of information for each one of these cancer-causing agents that we'll discuss. They're outlined quite nicely in the book, so if you have your outline done and it's a little thin when it comes to these substances, you need to fill in by paying attention to the video. I also have some other added material to show you when it comes to these different substances. So we are on page 389 in your textbook. If you'd like to follow along or take some notes, that would be a very, very good idea. I'm spending a lot of time on these things because these are the important chemicals that get asked on both the ACE and the AP exams. So I'm going to switch to the PowerPoint presentation and we shall begin. Okay, you can follow along in your book, and the first heavy metal that we have to discuss is lead. Now, we have known for about 50 years now that lead is cancer causing, and not only does it cause cancer, but significantly it causes mental retardation, developmental delays in little kids so that they can't learn as well as they ought to be able to learn, and other severe learning disabilities. And we discovered this by accident. One of the substances that had a lot of lead in it back in the day was paint. And so people painted their houses, and one of the problems with paint back in those days, the paints weren't nearly as good as they are today. After a while, those paints would chip off of whatever wall that they were painted to, and lead and the paint itself had a very sweet taste to it. We discovered this mostly in low-income housing and places like that. Little kids would inadvertently, you know how little kids are, put these paint chips in their mouth, maybe even ingest them, and then later on we discovered that these kids were having trouble in school, started to do a whole lot of analysis, and discovered that they had higher than, well, they had very high lead amounts in their bloodstream. Yes, it was in their bloodstream. So it was a bad situation. We outlawed lead in paint, and we've outlawed lead in a number of other substances that you might still come in contact. Usually it's older homes. For instance, homes that have copper pipes. Oftentimes copper pipes were welded together or soldered together with lead. There was lead in the solder, and so to this day in older homes, as water goes through those pipes, and that includes your drinking water, it goes right through the copper pipe, goes right past the lead that's in the solder, and so unacceptably high levels of lead were found in drinking water. Lead also affects pregnant women and their fetuses. So we've done a pretty good job of outlawing lead here in the United States and keeping it away from people and in homes. But of course, that doesn't count for around the world. So once again, in the developed world, where they don't have such, I'm sorry, I should say in the developing countries, where they don't have such stringent guidelines, people still encounter lead in their daily lives, and that leads to problems mostly with little kids. Brain damage, liver damage, kidney damage, and even cancer. So that's the lead story. Not much of a problem here in the US, but around the world still exists. You need to know where the problems come from. In our case, it would be pipes and paints, and what the health risk is to that particular chemical. All right, arsenic is next. Arsenic is a carcinogen, a known carcinogen. and it occurs naturally in rock formations. And we have discovered arsenic in the drinking water, because when you get your drinking water from groundwater, from an aquifer, if that rock formation that forms the aquifer has arsenic in it, then the arsenic ends up being in the drinking water. These everyday water filtration systems that you have at home do not take care of arsenic. In addition to that, we discovered mining operations would free up arsenic that was sort of locked in rocks, and so during the mining process, the digging up and the breaking up of rock, arsenic was released, and that would end up in the drinking water. Some industrial uses and even wood preservatives have arsenic in them. Arsenic is associated with cancer of the skin, lungs, kidneys, and bladder. And these illnesses can take up to 10 years to develop after exposure. So arsenic is a pretty nasty chemical. Over the course of the last 50 years or so, we've seen a dramatic change in what the government considers safe arsenic levels in drinking water. Because every time we lower the standard, we discover that there are still people becoming sick from arsenic poisoning. And eventually, the standard has come way down to practically zero when it comes to discovering arsenic. So we have two problems with arsenic. It's naturally occurring. It's not just a problem in the drinking water because of human activities, but it can also be there quite innocently just because of the type of rock that the groundwater formation has around it. Mercury, that takes care of arsenic. Mercury is another naturally occurring heavy metal, and you've probably all heard about the dangers of mercury. In fact, I doubt that you can find a thermometer that you buy in a store that has mercury in it today, because we don't want people exposed. Special precautions are taken even when you deal with fluorescent lights, because old fluorescent lights have mercury in them. So if you ever do take one of those long cylindrical tubes out of a light fixture, they need to be disposed of specially at the landfill and not just thrown in the garbage. Now, mercury is a particular problem because it affects you right in the brain. So mercury, aside from being a carcinogen, really causes developmental delays, has big impacts on fetuses for females, and is very, very dangerous. Mercury, as you recall from the non-renewable energy chapter, mercury is released when we burn coal. But mercury can also be just naturally occurring Hg in the environment. The mercury that we release when we burn coal is small amounts. In fact, even when we burn garbage, there are a lot of places in our country that incinerate their garbage rather than landfill it. And so there's mercury in that smoke as well. The manufacture of cement is another source of mercury. Petroleum exploration releases mercury. And as I mentioned, inorganic mercury, plain old Hg, is not too much of a problem in and of itself. But when that inorganic mercury combines with other chemicals in the environment, it can be very, very dangerous. And the mercury compound that's most dangerous is called methyl mercury. Now, methyl mercury has a real brain impact, central nervous system, and particularly harms young children once again. All of these chemicals harm young children because of the fact that their bodies haven't developed yet. And so they have significant impacts on children as they grow up. You know, for adults, it's not nearly the problem that it is for children. All right, where do we have our big exposure to mercury? Here in the United States, most mercury has been banned. There are small examples of places, older buildings perhaps, that still have mercury products in them. One that comes to mind is old light switches. If you've ever been in an old house and you've turned on the light switch and you hear that loud clicking sound when you turn light switches on and off, those light switches have mercury right in the contact between the wires. So that's releasing tiny amounts of mercury every time you flip the switch. So it's a good idea if you ever are in the position to buy an older home to replace those switches. It's inexpensive to replace a switch, and it's definitely worth it. Now, mercury, not such a problem here in the United States, but it has become a major issue in some of the developing countries, especially those whose diet relies primarily on aquatic animals, fish, shellfish. You can think of China, Japan. These are countries that eat fish not just once a week, but they rely on fish almost on a daily basis. Here's why it's a problem. This methylmercury is found in large amounts in ocean waters, and because shellfish are filter feeders, that methylmercury that's in the water accumulates in the tissue of the shellfish. Likewise, it accumulates in the tissue of the fish, and so there can be high levels of mercury in fish and shellfish. It's a problem in other parts of the world to such a great extent that people have to monitor closely how much fish that they eat, and that's a problem in a country like Japan, where so much of their lifestyle revolves around the eating of fish. The EPA protects us with guidelines and regulations concerning the amount of mercury that we're allowed to have in our fish. But remember, small fish eat larger fish, and so the large predatory fishes, especially the very large ones, have even more levels of mercury in them. Even you guys, if you eat sushi, are exposing yourself to more mercury than you should ingest. And I think in the book it said if you have 6 pieces of sushi per week, you are probably exceeding what the EPA is safe for you to ingest when it comes to mercury, even here in the United States. There is a disease associated with mercury that I will cover in another chapter, but if you're interested in knowing it, it's called Minamata disease, and it has been covered on the AP exam before. Minamata disease is basically mercury poisoning, and it is a major problem in the countries of China and Japan. Alright, that's mercury. Now let's talk about acid deposition and acid mine drainage. This problem, of course, occurs because of mining activities, and so not much of an issue if you don't live near a mine. But because mining activities oftentimes end up depositing those tailings in nearby water, we end up with dangerous levels of chemicals from mine drainage in drinking waters. Dry deposition occurs, wet deposition occurs. Acid deposition will be covered in another chapter in terms of acid rain, but as you see from the word acid, what we're talking about here is extremely low levels of pH. And when a low level of pH happens and you're exposed to it, your body has to try to buffer that acid that you've added, and that can put a strain on your system. Mostly acid mine drainage and acid deposition in general are environmental problems. They affect small lakes, ponds, and places like that lower the pH to a point where fish can't even survive in those waterways. And there's a nice picture of acid mine drainage to let you see how nasty that looks. I'll show you that in a minute. Okay, now for the synthetic compounds. These synthetic compounds you need to be familiar with, at least in terms of their names. For instance, I think I've already told you the story of DDT. DDT is a pesticide, and it has high persistence in the environment. That means it does not break down. So DDT that was sprayed 50 years ago as a pesticide on some farm is still there, and it's causing problems. These synthetic synthetic compounds are toxic. They cause genetic defects, and so they represent a real harm to humans. That's why DDT's been banned here in the United States. You also know the story of DDT when it comes to bioaccumulation, and that was the story of the top predators, the birds of prey, like ospreys, even our friend the bald-headed eagle. These large birds of prey the females had problems laying eggs of the appropriate thickness because DDT was affecting the thickness of the egg. So babies were dying prematurely in the nest because of DDT. Other compounds we find in our drinking water. This was alluded to in the video that you watched the other day. Human hormones and other chemicals that end up in our pharmaceuticals. You know something that probably you do at your house when you have an old bottle of pills and you haven't used them all and they're out of date. You often hear the recommendation to flush them down the toilet. Well, if everybody's flushing drugs down the toilet, we have no effective way to filter out these chemicals from the water when it gets to the sewage treatment plant. The video that you watched yesterday. So these chemicals, in some cases they're hormones, end up in the water supply, and they have an effect on the aquatic organisms. And there have been examples of species of birds, water birds, and species of fish that have developed very strange problems. For instance, hermaphrodism, in which the males and females seem to have some gender issues. We need to be concerned with what's ending up in our drinking water when it comes to hormones and pharmaceuticals. On military bases, because there's a lot of industrial activity on military bases, one common chemical that ends up in the drinking water are perchlorates. And this happens mostly in places where rockets are manufactured or rockets are used. Primarily, humans are exposed with contaminated food or water. They affect the thyroid. And then we have industrial compounds, and in particular PCBs, polychlorobenzene. I don't think you need to memorize what the letters stand for. In the book, it's polychlorobiphenyls. The problems are the same. Highly carcinogenic. Ingested PCBs can be lethal and can cause cancer. PCBs are used in many manufacturing applications. The making of plastic, insulating electrical wires and transformers. PCBs were used in all of these things. Now there's been a big decline in the amount of PCBs, once again because the EPA government has lowered the standard of what's allowable and acceptable in our drinking water. PBDE, polybrominated diphenyl ethers. They're used as a flame retardant, and so we find them in clothing, in electrical components, and sometimes we've detected them in unexpected places like in fish. Surprised to find them in fish and in birds, and can cause brain damage, especially in children once again. Most of the countries of Europe have banned PBDEs. We have not, although some of our states have. But we are monitoring the use of PBDEs closely. Okay, I have a few of these pictures and diagrams to show you. One of my favorite examples of a contaminated river is the Cuyahoga River that flows through Cleveland, Ohio. And this picture here is in your book. In 1952, it really was the first dramatic picture that we had of an area that is being damaged environmentally, and oh my gosh, we ought to do something about this. A river literally caught on fire. And it's just because of all the factories, all the manufacturing, all along this river were dumping all of their stuff. And back in the 50s, there were no regulations or rules against it. And the chemicals that were in the river were so much that one spark lit this river on fire, literally. Some have said that this started the whole environmental movement when we saw this on the news back in the 50s. Here's a great picture to let you know that pesticides don't really land on their designated targets. There's no pest in here that they're trying to kill, but these crop dusters are flying their mission, and they were spraying the crops, I'm sure, in this area and in this area. But that pesticides, they don't always end up where they're intended. Oh, and by the way, look at these houses. Isn't that nice? These houses are getting a nice dose of pesticide. This picture's in your book as well, acid mine drainage, and you can see the acidic nature of the sedimentation that ends up after a mining activity, ends up in a local stream, and there's nothing alive in that stream. The pH is too low. Organisms do not tolerate changes in pH very well. This is showing you where in the United States we have large amounts of arsenic. You remember arsenic is naturally occurring, but it's also common wherever there are rock formations, digging, things like that. Arsenic concentrations go up. And you can see where they've been particularly high, the blue. Not so much a problem here in Florida. Well, we don't do a lot of digging, a lot of mining. But in areas where they do, you can see certain pockets of places where the arsenic level's extremely high. This diagram here, or this graph, shows you where the mercury problems are around the world. You can see that we don't have too much of a problem here in North America. Europe and Russia a little bit higher, but by far the biggest piece, the biggest problem for mercury is in Asia. And again, inorganic mercury, not a problem, but methyl mercury that occurs in the environment bioaccumulates in the tissues of fish and shellfish. This last graph shows you frequency of contaminants in streams in the United States. And you can see that over 80% of the time, some sort of steroid is found in our streams. It's a dangerous situation here, guys. These prescription drugs, even non-prescription drugs, you know, aspirin, ibuprofen, stuff like that, showing up in large quantities in our streams. Of course, it unbalances the ecosystem, causing damage to plant life and animal life. Alright, if you'd like to take a little break and put this thing on pause, you can. I'm going to continue on. But this is another section in the chapter, so now I'm on page 394, and I want to talk about oil as a pollutant. And you might think that the catastrophic ocean pollution that we see from oil is from these terrible oilers, accidents that happen at sea, whether it's the Exxon Valdez or whether it's what was that called, the Blue Horizon in the Gulf. But you need to realize, even though those catastrophes are huge and it gets a lot of news and a lot of attention, I want you to take a look at what actually is adding oil to the oceans. 62% of the oil that's in the ocean is naturally occurring. It seeps out of ocean beds and places like that. And then we add a lot of oil ourselves just by the usage of petroleum products in our daily lives. The process of extracting the oil is a big deal, and really only 4% of the oil pollution that we see in our oceans is caused by tankers and damage to pipelines and things like that. What we have to be aware of is the little tiny drips, the trillions and trillions of little tiny drips that occur in our oceans are far more polluting than the big catastrophes. If there's one thing I can get you to take away from this section of the book, it is that the catastrophes that get the most publicity aren't necessarily the things that are doing the most damage overall when it comes to our oceans. Here are the sources and the problems. The big effect that we have with oil spills is the problem that the fish have, because if they come up near the surface, remember, oil floats on the water, so it's not a problem of sinking down to organisms that spend most of their lives down deeper, but for organisms that are near the surface. First of all, for the fish, that oil can end up in their gills, and they have no way of clearing out that oil out of their gills, and so it's pretty much death in a few hours when oil gets in the gills of fish. The loss of insulation and buoyancy for animals that live near water, and you're well aware there are a lot of species of organisms that live near water, particularly birds. And there's a picture in the book of birds that have oil on their feathers, on their wings, and again, there is no way for these birds to get that oil off of their wings, and as a result they have no buoyancy, so these water birds that are used to floating around on top of the water sink. They cannot survive. Of course, if a bird flies, all that oil on its wings make it unable to fly. And the only real remediation for these organisms, for the animals that live near the water and for the birds, is to wash them off. And when there is a catastrophe that we know about, you'll see volunteers actually go to the shoreline and help clean up these animals one by one, washing the oil off of their fur or off of their feathers. Of course, it can have a significant economic impact. There are several different ways that we can deal with oil spills. We can divide them up into two groups: the mechanical cleaning and the chemical cleaning. Mechanical cleaning is just about scooping up the oil. Because the oil floats on the surface, it does give us an opportunity to sort of skim it up. And so we can do that. There's pictures that I'll show you of tugboats and things that pull two ropes, and there's a skimmer in between them, and you just kind of move the oil to a set location where they can then vacuum it up, use pumps to pump the oil off of the surface of the water. And sometimes they use things called blotters. It's not unlike that pad that I have in my classroom in case there's a chemical spill. you put these blotters on there. They're very absorbent, and these blotters absorb up the oil off the surface, and then they're disposed of in a landfill somewhere. We can also use chemicals to clean up oil spills. And there's two different ways we do that. We either help the oil congeal and coagulate to kind of turn it into a bunch of individual balls instead of a slick that goes across all of the water. Those are called coagulants. You spray those chemicals on the oil slick and it causes it to ball up, making it much easier to pick up later. And then the opposite of that is the use of dispersing agents. In smaller oil spills, we can spray these materials on there, and that helps the oil slick break up into smaller and smaller pieces. And basically, the pieces are small enough that they just disperse into the environment. They're not gone, that oil's not gone, but it helps the oil disperse and sort of dissolve into the water that way. Just remember, it's always still there. There is no away. Here's a picture of how the skimmers work. You can see the tugboats pulling, and it's just a series of plastic. You know, this is a lot like, have you ever seen the ropes that are used in swimming pools to outline the lanes, the swimming lanes in an Olympic-sized swimming pool? That's the same kind of material here on these skimmers. And in this case here, you're seeing after the oil is skimmed up, then we use these pumps to suck the oil off the surface. We've been through the Exxon Valdez before. I don't think we need to hit this again. So we have booms, dispersants, and here's another one that we have yet to mention. Genetically engineered bacteria. A great discovery. We've got chemicals that disperse oil. We know what they are. And we can trick bacteria into making that chemical. And we trick it by inserting the gene into their DNA strand. Remember, bacteria are very simple. They don't even have a nucleus. All they have is a strand of DNA. So it's easy for us to splice into bacterial DNA, add the gene that we want added, and that gene stimulates the bacteria to make the chemical. And so then we can spray the bacteria onto the oil slick, and the bacteria disperses the oil slick. You'll hear laymen talk about oil-eating bacteria. Well, they're not eating the oil, but they are naturally creating the dispersant that helps that oil slick dissolve. All right, that's about all I wanted to cover on oil. Of course, oil is a big danger to oceans, and this is not covered in the textbook, but I find very important for us to talk about when we talk about water pollution. You think a lot about rivers and lakes and streams, and we should because they're right near our house. But what about the middle of the ocean? What kind of pollutants do we find there? Well, the answer is not many. And the reason is because there aren't a lot of people out in the middle of the ocean. So there's not a lot of damage being done by our activities. So when you think of ocean damage and ocean pollutants, you should think of shorelines. The closer that water is to the shore, the more potential it has for pollution. And you can see all of these different sites, all of these different activities that end up doing damage in our oceans. We talked about red tides on Thursday, so we don't need to hit that one anymore. We've already talked extensively about runoff from pesticides or fertilizers, and of course that adds to these oxygen depleted zones. We talked about that and the big one that we have at the mouth of the Mississippi River. Shellfish beds that die off You know, we love to catch our clams, our shrimp, and so forth in beds that lie right along the coastline. Well, not if we are continually adding toxic materials into the ocean. And it gets to the ocean because that's how our street sewage system works. Now, when I use that word sewage, when we talk about streets, we should really not call them that. In fact, those grates that you see on the corners of streets, and when it rains you see all the water flow down into them, we'll call those storm drainage system. Because if you hear the word sewage, you should be thinking about human excrement in water. So it's really inaccurate to call those things sewers, although you probably have been doing that your whole life. Those are not sewers because they do not hold sewage. They do not hold excrement. However, the fact is that they are storm drains, and all of those pipes, I mean the ones under your street, the ones under my street, when we have a rain, all of those storm drains, they just pump. They don't even pump. They just go by gravity underneath your street to the St. Johns River. There is no filtration whatsoever. And so anything that's in the street, like for instance little drips of oil from your car that might be on your driveway, when a heavy rain comes, picks up that oil, it runs down your driveway, it runs to the gutter of the street, it goes down the storm drain and ends up in the St. Johns River. What are the chances that there are some toxic materials in that water that ends up accumulating right here along the shoreline? Since we don't live on the ocean, our drainage isn't going, it's going to the St. John's and it's not going to the ocean. But what does the St. John's empty into? The ocean. And where do so many of us love to live? Near the ocean. Where are so many different factories? Pulp and paper mills. You find them all up and down our coast here in Florida and up into Georgia. So these different places are dumping directly into the oceans. Let's take a look at a couple videos. I'll tell you what, we'll watch those videos in class. Remind me to show those to you in class. I think I've covered all of these different issues that are on this diagram. Real important for you to understand all of the different threats that occur to our oceans and our beaches. And one that we have not, I didn't cover yet, but we did in another chapter, ocean acidity, caused by an increase in carbon dioxide in the air, and that chemical reaction that occurs with carbon dioxide right there at the interface of the air and the water causes the formation of HCO3, carbonic acid. And so we are seeing, especially near the coastline, where there's a lot of CO2, higher amounts of CO2 than out in the open ocean, an acidified ocean. And as we've talked about so many times, organisms cannot tolerate changes in pH. Real quick, let's just go through these other water pollutants that occur. Obviously, we have a problem with solid waste. And again, in areas around the world where people live right on the water, and in so many places that's true, they have a poor job of dealing with their solid waste, and so they end up dumping their garbage in the river or in the lake. There's sedimentation that occurs, especially when we mess with the natural flow of a river or a stream. We have siltation, the buildup of sand, silt, or clay that dumps directly into a larger body of water like an ocean. Thermal pollution is about temperature and heat, and again, our activities, especially when it comes to factories Oftentimes factories need to use water in their processing, but that water is really, really hot. And so they're dumping that hot water back into whatever body of water they got it from originally, causing problems. The organisms can't tolerate having boiling hot water piped back into a lake or a stream, and so there won't be very many living things in that region. And then in the book they mention noise pollution as another type of water pollution. And what we're talking about here basically is the disturbance that our activities can have on organisms that rely on sonar to communicate, like whales. And if we have too much boating activity near the shoreline, our use of sonar, our use of long distance radio waves can interfere with their ability to communicate with one another and do damage to them and decrease their numbers. There's a nice picture of garbage for you. Obviously garbage in our waterways is mostly a problem in developing countries. Ever since the 70s, we've been pretty vigilant about littering, just throwing garbage into our waterways, so we don't do much of it anymore. A nice picture of how sedimentation can affect the oceans. Do you think that there's a lot of shellfish and fish in this area of the ocean? Absolutely not. And all this sedimentation is coming down because we have changed. We've put up these barriers, these levees, all the way down the line, and so the natural flow of the river cannot occur. The siltation that ought to be in this large area here, this large area probably ought to be the river delta, but because we're living there instead, all of that soil from the delta ends up in the water, goes down this man-made levee, and ends up pouring into the ocean. And the picture of thermal pollution, that's in your book on page 398. That, my friends, is the end of this video. I know it's a long one. We've got one more to do from this chapter. We need to go through the laws. You need to be familiar with the laws because there are about 20 of them for you to memorize, and you haven't memorized very many of them yet. Well, this is your first opportunity to really get into the different laws that we use to protect ourselves from water pollution. That's it for now. Have a good weekend.